Yeah, is he hearing anything? Okay. So I notice on my screen, if I put the polarizer vertical, I can see through it. If I put it horizontal, I can see through it. But in this way I can see through, but this way I can't. So they've polarized it at a 45-degree angle. So I can read books either vertically or horizontally, I guess. Okay, here we go. So is everybody here? Close enough anyway. Okay, so today we're going to do a little overview of radiative transfer theory, which is, the underlying physics and mathematics for all of optical oceanography and ocean color, remote sensing, and all of that. So basically I'm going to walk you through kind of how it works. We're not going to dig into the math, at least very far, maybe a little bit at the end. We'll derive something called Gerson's law. So anyway, as I said, it's the mathematical and physical framework for everything we do in this class, so you need to at least see a little bit about it. I'm going to say a few more words about polarized light and how it fits into the equation, so you see what's going on there. Then I'm going to go basically outline how you get from fundamental physics to radiative transfer theory. And we're going to see the radiative transfer equations at various levels of approximations along the way, finally ending up with the equation that hydrolight solves. And then, time permitting, we'll get into some solutions here of how you can actually solve the equation for very simple cases. Okay, so back to our chart here now. Once again, we've played here, we've played down here, we played here. Now we're going to look at the radiative transfer equation, which, as you see, takes IOPs and boundary conditions and puts out radiance, and then from that you get all the irradiances and all of the AOPs. And technically it's not the radiance you need to know, it's the Stokes vector, the first component of which is the radiance if you don't worry about polarization. I did have a couple of little videos here which didn't work on Ken's Mac, but if I can figure out where's my cursor, here it is. That's just a view of linearly polarized light if the beam's coming this way, so nothing fancy there. But this other one shows you, whoops, what Ken was showing you. Like, here's the red light wave, and if you're sitting at one spot, you'll notice as the electric field vectors go past that spot, they tend to rotate clockwise. That's my convention for right circular polarization, and that's what Craig Boren uses in his book. But as Ken warned you, other people will call this left circular, and it seems like astrophysics people have one convention, the chemists use a different convention, then the atmospheric people are back to my convention, etc. So just be forewarned when you start reading papers and people will say, well, I measured the right circular polarization and here it is, and it looks wrong, but compared to some other paper, they've probably used different conventions and they didn't tell you which one they used. Okay. When we are going to treat scattering by polarized light, so we'll have the incident Stokes vector here, which might be polarized, might be unpolarized, but just in general. Stokes vector comes in, interacts with a particle, and gets scattered off in some other direction through a scattering angle psi. Well, as Ken showed you today, you start out with the Stokes vector, it's going to get multiplied by a 4x4 matrix and end up with the scattered Stokes vector. And of course the scattering angle is given by our old friend here that we learned the other day. Okay, then of course scattering can change one state of polarization into another. It can change unpolarized light into polarized and so on. So that's what those four elements do. Now this, as I've written it here, the Z matrix is called the phase matrix. And we have to get into coordinate systems now. Ken briefly mentioned that you've got a coordinate system here, and then you have to have either, I called it horizontal and vertical, he called it perpendicular and parallel. But you have to pick some coordinate system. And keep in mind that one person's parallel direction is somebody else's perpendicular direction. So once again, you have to, in a paper, tell people, here's how I define either horizontal and vertical, or how I define parallel and perpendicular, and then they know what your coordinate system looks like. And it seems like about 10% of papers actually do that.
Some little trivia thing?
Yeah.
In the old days, in the 1910, 1920, when people were describing polarization of light field, they talked about they did it in terms of the magnetic field, not the electric field. And so you read there, and until you figure that out, everything's 90 degrees from what you should think it should be. But they don't really say it, because that was the convention. Everybody talked about the magnetic field. Now
Yeah, and the British still sometimes do everything in terms of magnetic fields, and Americans and everybody else do it in terms of electric fields. So it's a mess. Anyway, in the ocean or the atmospheric work, we always reference things to what are called meridian planes, which is defined by the z vector and then the direction the light's propagating. And I showed you a figure where he was interested in skylight. Skylight's coming down, so he had a perpendicular direction, and his parallel was this way, and perpendicular cross parallel was going downward towards the origin. I'm now picking perpendicular and parallel, so that perpendicular cross parallel is going that direction. In any case, the normal thing is to say perpendicular cross parallel is in the direction the light's propagating. So Ken's looking at skylight going down, I'm looking in this coordinate system at light going that way. And so you then have to pick this coordinate system. Your Stokes vector is then defined in that coordinate system. Now the problem comes is if this light comes along and it scatters into another direction, then that's a different meridian plane. So here's just a horrible drawing, but we start out with light going in the direction of the red C prime vector. So I'm going to have an instrument over here looking at that and measuring the S prime Stokes vector. But then it gets scattered. Let's say there's a particle here, and it scatters it off into the final C direction. And I'd have an instrument up here looking and measuring that. But now the Stokes, the meridian plane is from the Z axis to the final direction. The incident or initial meridian plane is from the Z axis to the initial direction. So that's a real can of worms to keep that algebra or the geometry straight. And so when I write that the final Stokes vector is the initial times this Z matrix, that's with respect to these meridian planes. Then what people do is they say, look, let's write this phase matrix as a geometry matrix times Ken's Mueller matrix times another geometry matrix. So there's a thing called the scattering plane, which is in pink here, and that's the plane that's defined by the incident and the final directions. So what you do is you take your initial Stokes vector, it's in this green initial horizontal vertical direction, you rotate those guys around into a direction that's perpendicular and parallel to the scattering plane. Then you multiply by Ken's Mueller matrix. That gives you the scattered light over here in the blue S and P directions, and then you have to rotate those directions into the final green horizontal and vertical. And you don't want to see the equations, trust me, but that's the way it works. So when you have an equation that looks like this, Z is called the phase matrix, and it's the product of actually three matrices. So what you're doing here is splitting off the actual physics of scattering from two matrices that take care of the geometry. So that's the idea. Okay, and I just want to show you that so you know this is how it works when you go read a paper on polarization. That's what's going into it. And you'll see these kind of figures, and there's all these like dozen different angles here, and it's a real mess. Okay, so enough said there. I think if you want to see the equations, there's a couple of pages on the web book, and you know, it goes into this and it shows you these various matrices. So as Ken said, you know, why do we care? Well, polarization, as we are slowly learning, it's affected by the size distribution, the shape, the index of refraction, and all of those things. And so you can extract information about what's going on in the water if you measure the polarized light field. And that's what's, I think, certainly the future coming down in the next decade or two. Most of what's been done in oceanography to date has ignored polarization. And the reason is, well, you need to measure a 4x1 Stokes vector and a 4x4 scattering matrix. Well, it's hard enough just to measure the volume scattering function, the 1,1 element of the matrix. There are no commercial instruments you can go buy and throw in the water, and out comes the Mueller matrix. So even if we do the math of all the polarization, you don't have the input to go into the equations when you want to solve it. Now, maybe 20 years from now, there will be some nice instrument you can put in the water and it comes back with the Mueller matrix. But time will tell. Okay, polarization is thought to have little effect on processes like phytoplankton photosynthesis. The phytoplankton doesn't care what the polarization state of the light is. It just grabs a photon and does its chemistry. So at least that's the belief. Different polarizations and radiance of radiance in different directions tend to average out when you compute in irradiance. And this is what saves hydrolight. So in the real ocean, if I look in this direction, you know, there's one state of polarization, and I look here, there's a different one. Look over here, something different. But then when I integrate over all of those directions and I get an irradiance, in hydrolight, it might be 10% too big in this direction and 10% too small in that direction because it ignored polarization, but then the plus and the minuses tend to add out, and I can still get an irradiance that's good to 1% or 2%. We don't have the measurements. We also don't have good models that I would need to say, I can use me theory and compute the 4x4 Mueller matrix for spherical homogeneous particles, but you know, how applicable is that to some real phytoplankton and real mineral particles that are not homogeneous, not spherical, etc. So anyway, this is why in this, or one reason in this class, we don't do much with polarization, but you still need to know a little bit about it. Okay, so Colin, in her first lecture, gave you what's called a phenomenological derivation of this, what's called the scalar radiative transfer equation. And the term vector equation means it includes polarization. Scalar means it ignores polarization. So what she did was she defined radiance, and we talked about how I can have this Gaussian tube and it collects the energy that comes in, blah, blah, blah. And then we make arguments about conservation of energy as expressed in terms of radiance. So you looked at, you know, light comes along, some gets absorbed, some gets scattered out, some gets scattered in. That's all basically writing conservation of energy in terms of radiance, and then she ends up with this equation. Now, if I can make an analogy here, if you assume the Earth is at the center of the solar system, you can explain an awful lot. That's what Ptolemy did in the 2nd century AD, and that worked quite well until Galileo took a telescope and looked at Venus and saw that it had phases. And he knew at that time that the whole Ptolemaic system was wrong. It's this Copernicus guy that got it right. It's really the sun that's at the center and the earth goes around it, not the other way around. So if you're NASA and you're going to send a satellite to Mars, you need to do it right. Put the sun at the center of the solar system, let the earth and stuff go around the sun. But for the average guy on the street, he's okay assuming the earth is at the center of the solar system and the sun goes around and the moon goes around. Yeah, everything works okay, because he's not looking at Venus through a telescope and he's not sending spacecraft to Mars. There's a similar thing here. At our level of what we're doing, the phenomenological derivation works fine. You get an equation that works pretty well. And phenomenological means you don't tie things to the basic physics. You look at some physical phenomenon, you cook up an equation that describes it, and it may work quite well or it may not. And it might even be the correct way of viewing it, you're not sure. But anyway, you're getting a decent answer and some kind of intuitive level of understanding of what's going on. And there's a lot to be said for that. On the other hand, if you really want to be very rigorous, you have to go back to fundamental physics and come through some process and end up with your equation. And then you know how you fit in to the grand scheme of very exact, rigorous physics. So I'm just going to kind of walk you through this today. So in our case, what you would do is start with Maxwell's equations, which describe light as propagating electric and magnetic fields. And then there's an enormous amount of physics and math here that was only worked out in the last 10 years by a fellow named Michael Mischenko. And he ends up with what I'll call a general vector radiative transfer equation. And then you can simplify that. We're going to walk through that. And guess what? You end up with the same equation. But the understanding is deeper and the interpretation's a little different. And in particular, to get from here to here, you never define radiance and you never make an energy argument. It all drops out of this hardcore math and physics. So anyway, what we're going to do here qualitatively is we've mentioned quantum electrodynamics before, and from that, we think that's really how light actually works. You can make predictions from QED that have accuracies compared to experiment of order 1 part in 10 to the 12th. That's equivalent to measuring the circumference of the Earth to within 0.04 of a millimeter. It's phenomenal accuracy. One of those predictions may take a year or more of computer time to do the calculations. So it's correct, it's not too useful for everyday life. But from QED, you can get eventually derive Maxwell's equations. That was basically Nobel Prize level work by Feynman and others. You can now, in the last 10 years, we can go from Maxwell's equations down to a radiative transfer equation that is the sort of thing I work with. And it was phenomenally difficult. The derivations are like, 100 pages of math and almost incomprehensible to more than 5 people. Then you get this, what I'll call general vector radiative transfer equation. You can simplify it to particles that have mirror symmetry, and we'll talk about what that is. So a good PhD in physics could probably get from here to here, and we'll sort of start here, and then things get simpler after that. But that's how you start from fundamental physics and get through to hydrolight. And so physics is now, radiative transfer theory is now considered a proper, rigorous part of the mainland of physics. Okay, so I said enough there. I think there's a webbook page or two that goes into a little bit more about how QED works, and there's a couple of webbook pages on Maxwell's equations. If you're a physics major, you've seen them. If you're not a physics major, you wouldn't understand them if I showed them to you, because it would require like a month of background to get to them, so no reason to look at them. But Basically, here's a statement from a quantum mechanics book that says the classical limit of the quantum theory of radiation, that's QED, is achieved when you have an enormous number of photons so that the light can be considered a sort of continuous something rather than a lot of little pieces, which are photons. And so the classical electromagnetic wave, that's Maxwell's equations, approximates the behavior of trillions of photons. So that's how it all ties together. And so then Maxwell's equations work perfectly well for everyday problems. So if you want to build a power plant, generate electricity, you want to make a radio, you want to, talk about refraction and reflection of light at the sea surface, you want to talk about scattering of light by phytoplankton, all those kinds of things, you can all do with Maxwell's equations at the level of electric and magnetic fields. But that's still way more information than a biologist needs. They just need to know how much energy did my phytoplankton absorb. I don't care what the electric field and the magnetic field on the phytoplankton was and all of that. So even if Maxwell's equations were easy to solve, they give you a different kind of information than we really care about. And you could take those electric and magnetic fields and compute the energy from those, but that's more effort than is necessary. Maxwell's equations do eventually break down if you're at extremely high energies or at the atomic scale and or very low temperature, and then you have to go back to what's dealing with individual quanta. And when you see words like photonics or quantum optics, that's what's going on there with the people that play with very powerful lasers. Okay, so anyway, you go through all this math and you start with Maxwell's equations, you look for this propagating wave solution that Ken talked about briefly, and you eventually get an equation that looks like this. Okay, this is three-dimensional in space, so I've got the direction of the photon is direction c, and this c dot grad is the directional derivative in the three different directions, x, y, and z. And we'll simplify that. In a one-dimensional geometry, this will just become a depth derivative. Okay, so anyway, you've got this spatial derivative of the Stokes vector. Then here's the Stokes vector times a matrix K, which is called the extinction matrix. Now that's another 4x4 matrix. And in general, different polarization states are attenuated at different rates. So in general, meaning let's say you've got a crystal or you've got some material where the particles are not randomly oriented, they're all in this lined up in this direction but not this direction, then this state of polarization will attenuate differently than this state. So in general, this 4x4 extinction matrix has all 16 elements non-zero. And then here's our Stokes vector, here's our phase matrix scattering from the initial direction to the final direction, integrated over all solid angles, and then there's a source term out here. So if I put this laser in the water, it's putting out polarized light, and that'll be described by this source term. Okay, we start out with this general matrix, different extinctions for different polarization states, and the scattering here is a 4x4 matrix, and in general, all 16 of those elements are non-zero. Okay, we need to get something simpler because this equation, even though you can solve it mathematically with enough computer power, you don't have these inputs. And in the ocean, we just don't need that level of complication. So what do we do next? Well, if you assume that the particles that are doing the scattering, whether they're phytoplankton or air molecules or whatever, if you assume they're mirror symmetric, life gets a lot simpler. So what's that mean? Well, here's a particle here. So this is some little diatom or whatever. And this is a mirror. So if you reflect this particle in a mirror, it looks like this. And then if you can rotate this particle some way and it looks like what you started with, that's a mirror symmetric particle. Now here's another funny looking little diatom, let's say with a little head here. You reflect that in the mirror, but then no matter how you rotate it, you cannot get this guy to look like what you started with. So that's not a mirror symmetric particle. So here's a bunch of diatoms, cute little guys. You'll notice that all of these have some plane of symmetry where if you flip them in a mirror, they'll look just like what you started with. So, and here's another one here, close enough that if you flip this guy about this axis here, okay, this one little appendage is a little longer than this one, but you know, close enough. That's a good approximation to a mirror symmetric particle. So most of the phytoplankton and such that we have in the ocean are mirror symmetric. Now you'll notice a few of these could pass as spheres, but a lot of these guys are definitely non-spherical. So how good is me theory going to be when you apply it to this thing or this phytoplankton here? Maybe not so good. Okay, what happens? Oh, well, here's a phytoplankton. This is another diatom. This guy looks like a left-handed helix, and he is not mirror symmetric. If you flip a helix in the mirror, you can't rotate it and get back to the original helix. Now, I say it's left-handed helix, but maybe this photograph has been flipped. I don't know, in which case maybe the real thing was a right-handed helix. Do you know, Colin, if these are?
I don't know exactly sure, so I don't.
Yeah, it's from this guy, Wim van Egmond.
Yeah, and often some people see that, you know, with images, they flip them to sort of fit whatever.
Yeah.
So I don't know.
Yeah.
I think that they do come with different directions of spiral.
Yeah.
Just like you find in shells of gastropods.
Yeah.
And it means something if they're a right spiral or a left spiral.
Yeah. So in any case, if you had a bloom of these things, and they were all either left or right, whichever it is, then, you know, you'd have to go back to the full-blown equation. But if you have a mixture of left and right-handed things, then your medium on average is now mirror symmetric. And like I say, I'm ignorant of phytoplankton, but there's a case when you could not make this assumption. Yeah, Lydia.
If we could go back to the previous slide, mirror symmetric means that if you take a line in the middle and
Yeah.
take the mirror and turn,
Yeah.
it should fit. So doesn't that disqualify most of the things here?
No, because let's say if we just, let's take this one here. So here's this particle, let's say it looks like this, and we have a mirror, then this flips over and it looks like this now. And so then if I took this and I rotated, let's say by 60 degrees, this guy would go to here, this guy goes to here, this one goes to here, and then I have the particle that, what did I do? That the purple one looks like what I started with. So,
I understand the thought when taking a dissection or a mirror.
yeah, okay. In general, if a particle has some symmetry where you can pass a plane through it and it looks the same on the left and right sides, then it's mirror symmetric. Okay, so what's cool is if you have mirror symmetric particles, this attenuation matrix, which is a 4x4 matrix, it becomes diagonal, and the value of the values along the diagonal are all the same, and guess what? They're equal to the beam attenuation coefficient. So then for mirror symmetric particles, any state of polarization attenuates at the same rate, and the same rate is unpolarized light. And then the Mueller matrix, the scattering matrix, takes on this symmetry here, where there's really 6 elements. There's 1, 2, 3, 4, 5, 6, and then there's some symmetries across there. So our equation gets a whole lot simpler if we assume the scattering particles in the ocean are mirror symmetric. Okay, then here's Ken's data back from 1984, where he showed you this, and you can see I just kind of colored in the values where he's factored out the 1, 1 element. And so does this Mueller matrix, its actual measurements in the ocean, does it look like this symmetry here? So these would all be 0. This can be different from this one, but this one should be equal to that one, and so on. Well, here's that. Those 4 are all 0 to within noise. Those are 0. This one's equal to this one. This one here can be different from this one, and it's a little bit different. These 2 are equal. These should be anti-symmetric, but it looks like they're 0 anyway. So lo and behold, the measurements say that, yeah, it looks like the particles in the ocean that day were mirror symmetric. Now, the fact that this one is not 1 is telling you that there are non-spherical particles there. So, okay, I can believe that. So anyway, we now end up, and also if we look at a one-dimensional geometry, so things are horizontally homogeneous, but they can vary with depth, then our gradient just becomes cosine theta times the depth derivative of the Stokes vector. And now what we end up with is a depth derivative. We now have just beam c times the Stokes vector, and now we have this simpler Mueller matrix, and this is what these rotation matrices look like. So I take my incident Stokes vector, rotate it from the incident meridian plane into the scattering plane, do the scattering in a scattering plane, rotate that final scattered light into the final meridian plane, and that's what's going on in that equation. Okay, so the atmospheric optics people do routinely deal with polarization. It's mostly the underwater people that have ignored polarization. So there's lots of people that work with this equation right here, and the atmospheric people usually get their Mueller matrices from me theory. And they take aerosol particles and water droplets and all of that, and they do me theory, and they get what they need here. Okay, and there are people like Howard Gordon and George Kadawar who have Monte Carlo codes that work on this equation here. The catch is they're not available. They're proprietary codes, so you can't get them. But anyway, when Howard Gordon publishes a paper and he has actually coupled atmospheric ocean code that has the polarization in it, that's the equation he's solving right there. Okay, now I'm just going to be interested in unpolarized light. That's enough for me. So how do I get that? Well, that's the first element of the Stokes vector. So I'm going to take this matrix here times an IQUV. So it's going to be M11 times I plus M12 times Q, and then 0 and 0, and then away I go. So here's, and sorry, I have to put these guys in there as well, and they end up giving me also the second guy times the Q and U terms, because this thing, when you multiply this and then multiply times another matrix, that mixes all this stuff up, and it's just then a big ugly matrix. And then you can, take that, take the product of the 3 matrices, multiply by your incident Stokes vector, and get to the final one. So if I'm only interested in the 1, 1 element here, the unscattered radiance, then okay, there's my C times I, and in this class we usually call I L the radiance as opposed to just the I element there. But then we pick up the M11 term times unscattered, and then a source term for unscattered part. And then there's these rotation angles get in the mixture, and we pick up an M12 times Q, and then there would be a source term for that state of polarization, and an M12 times a sine times the U element, and a source term for that. So we end up with this equation for the unpolarized radiance. The problem is I can't solve this equation because it involves these two states of linear polarization. So I only want this part, but I still have to solve the whole vector equation to get these parts just in order to pull out the unpolarized part. Because what these are doing is turning polarized, linearly polarized light into unpolarized light. So I'm screwed. I can't come up with an equation that's just for unpolarized light. So what do? What did I do 35, 40 years ago? You just say, I can't handle these terms. Let's just throw them out and hope for the best. That's honestly what's done. So then you end up with this equation here, and this is the volume scattering function. That's the equation that you get from the phenomenological derivation that Colin gave you. And from that derivation, you don't necessarily realize, oh, there actually are these other terms in here. Now, if I ignore those, how big of an error is that? That's kind of important to figure out. So what we do is, there's just a page here that's saying there are some instruments out there for measuring the VSF, so that's the 1,1 term, or we call it beta in here. There are a few of the measurements or instruments around where people measure like the M12 and maybe the M22 terms, but those are, once again, they're not commercial instruments. People have just built them in their lab, people like Ken, and so we really don't have much data on this. So then, anyway, we come back now to, here's our scalar equation, and that's the equation that hydrolite solves. Yeah?
Is there a physical interpretation for the assumption we're making by throwing those two out?
Yeah, that's coming up. Okay, so at any rate, we've gone through a rigorous derivation, and we've said, let's just ignore these polarization terms and hope for the best. And then I've spent my entire career solving that scalar equation and hoping for the best. Okay, so what kind of errors can we get here? Well, you remember in the lab, or when you're looking at the sky, and the light's going this direction and it's scattered at 90 degrees, that's when the polarization's maximum. So if we go back to Ken's data, so here at 90 degrees, so here we're going from 1 to 0 and then scattering angle of 0, 90, 180. So here, for example, at 90 degrees is when this M12 element has its maximum magnitude. In this case, it's negative, but that's the maximum. So that's that most scattering at 90 degrees thing. So just kind of remember that this number is somewhere like 0.8 in magnitude. And then we come along here and we say, okay, observations in the ocean show that underwater light fields tend to be like 10 to 30% polarized. You know, remember Ken's degree of polarization was, or degree of linear polarization is what is the fraction of linearly polarized light to the total. And that tends to be 10, 20, maybe 30%. So I can say, look, if I take this M12 element at 90 degrees, that's the biggest value, that's something like 0.8. At worst, the linear polarization, depending on what direction I'm looking, that might be 30% polarized, so 3/8 is roughly a quarter. And then this is measured relative to the first element here, and the unpolarized light. So the fraction of this polarized contribution to the unpolarized part could be as large as 25%. So that kind of gives me the idea, if I ignore polarization, I go in the ocean, and I just happen to look in just the right direction, I might be off by as much as 25% by ignoring polarization. Now, in reality, I'm usually looking in other directions, and so the M12 element is going to be less, might be only 0.1 instead of 0.8, or it might be 0.4, and the light might only be 10% polarized in that direction. So in general, it's usually more like an error of 10% plus or minus. And there's been a lot of comparison runs done between using the unpolarized equation and using a fully polarized solution, and then comparing the light field in different directions, and you're usually off by like 10% or so. And George Kadawar, who's like the god of polarization, says the most common question he gets is, George, how far off will I be if I run Hydrolite, which doesn't have polarization, compared to running a code like yours, which does have polarization? And the answer is always, well, you'll be off by like 10% or so. And George and I wrote this big paper one time to compare polarized versus unpolarized calculations as a function of direction and what's in the water and sky angles and all of this kind of stuff. And we submitted it to 3 journals, and were never able to get it published. Every reviewer said, this is well known, this is trivial, there's no reason to publish a paper showing how big the errors are when you use unpolarized calculations. And so reject. We tried 2 more journals, and they all said the same thing. This is trivial, everybody knows the answer. Yet, the most common question Kadawar gets is, how big is the error, which indicates that it's not everybody who knows the answer. It's only the reviewers. Well, anyway, that's another story. So, bottom line is, even though the radiances might be off by 10 or 20%, they're too big in one direction, they're too small in another direction. You integrate over all of those directions, and those errors tend to cancel out. Yeah.
Is it still available somewhere else?
It's what?
Is that paper available somewhere else?
I think it's probably, our last version is on the computer in my office at home. And I keep thinking one of these days I will clean it up a little bit and put it on the web book, but I haven't done that yet.
George, you do something like that in the SPID?
Yeah, he probably did. Because this was Kadawar, and had a grad student named Yo Yu at the time, and we put all this together, and the reviewers just hated it. So after the 3rd journal, George says, well, we got to figure out where to submit it now. And I said, no, I'm done with this. I've wasted enough unfunded time on this, so it just died. Anyway, one of these days, when I have nothing better to do, I'll dig out that old paper and put it on the web books thing with some sarcastic comments about the reviewers. Okay, so even though this scalar equation is somewhat inaccurate, it's commonly used because, A, we can pretty easily get beam attenuation, and we can either model, or if you're really lucky, measure the volume scattering function. So we have the inputs that we do not have for the full-blown equation. The math is enormously easier to solve the scalar equation than the vector. And the output's good enough for many applications, although not all. And there's commercial software to do this, which is Hydrolite. There's no commercial software that you can get your hands on to do the vector equations. I have worked out the math to do the vector equation using the same type of algorithm that's used for the scalar equation in Hydrolite. It took me probably 6 or so months to do the math. There's a tech report, I think it's in your library there. It's 163 pages of equations. It was an enormously complicated problem. And at that point, I just didn't have it in me to start programming up these equations, which is going to be another 6 months worth of work. And that hasn't happened yet. So maybe someday there will be a polarized version of hydrolyte, but it's not there yet. And I may never get around to it. I literally, I would take, there's these charts that you write on, they're like pieces of paper, like a meter square. I would put those on the kitchen table, and with a pencil, I would fill an entire page of paper with one equation. And then I'd go to the, and then I'd simplify and cancel this term and that term and combine these two and whatever. And then I'd go to tear off the next piece of paper. That's how bad it was. Okay, anyway, so a little summary here, that Maxwell's equations are correct. They're just too complicated and they give us more information than we need. Here, there's a general vector RTE that would give us what we want, but we don't have the needed inputs for it. The VRTE vector equation for mirror symmetric media will be probably what we want for the ocean. And in the days of, when PACE is up there and people are routinely getting polarized water leaving radiances and all of that, that's the equation that we'll want to work with there. But still, we don't really have the inputs to do it yet. And so we're sort of stuck with this scalar level. And you just keep in mind that when you run hydrolyte and you look at a radiance, your error bars are plus or minus 10%, maybe 20%. But your irradiances are more like plus or minus 1 or 2%. And that's what most people in optical oceanography are interested in. Okay, I'll just put one slide here. Colin did the phenomenological derivation where she looked at light, unpolarized light coming in, and it scatters out and it scatters in and so forth. You've seen that. I put those like a half a dozen view graphs going through this again. They're on the back of this PowerPoint just so you have it for reference. And there's also a page on the web book that works through that. And this is what you'll find in every single textbook, whether it's light and water. Howard Gordon's new book is going to use the old phenomenological derivation. And we have a big round of conversations about, well, do you want to do it the right way? Do you want to do it the old way? And he said the pedagogical value, that is the teaching value of this derivation, outweighs the fact that it ain't really quite exactly right. And it turns out the real problem here is that when you formulate radiance, you talk about energy detected per unit time, per unit area, per unit solid angle, blah, blah, blah. Well, it's not really energy that interacts with matter, it's electric fields. And that means that the classical formulation of radiance is really not quite consistent with Maxwell's equations, which talk about how electric fields interact with charged particles. And the electric fields carry energy, but it's not the energy that interacts with the particles. Now that gets a little too philosophical for most people. I think there's like 4 people in the world that care, which is me, Howard Gordon, Mischenko, and maybe George Kadawar. But anyway, that's what's going on here. Let it go at that. So here's now our scalar radiative transfer equation written in terms of geometric depth. The name of the game when you solve this equation, no matter what technique you use, you have to put in the IOPs, beam C, volume scattering function, and if there's an internal source like bioluminescence or something, you have to put that in. You solve this equation and you get out what's underlined in red, which is the radiance distribution. Okay, so this equation in math speak, it's a linear, meaning the radiance is there only to the first power. First order, meaning there's only a first order derivative involved. Integral differential equation, because it involves integrals over what you're looking for, and it involves derivatives of what you're looking for. And so you give the green plus the boundary conditions, you solve for the red. And this is what's called also, that solution is a 2-point boundary value problem. So in other words, you've got the ocean here and let's say the bottom down here. So you're putting in radiance up here, let's say from the sky, and so what you start with has to equal the sky radiance, and then you compute the radiance throughout the water, and then maybe at the bottom there's some reflectance condition that says 15% is reflected, or maybe the water is infinitely deep, and so the condition is that the radiance as the bottom goes to infinity just goes to zero. But at any rate, you're going to use this equation, solve for the radiance throughout the water body, subject to the condition that at the surface you have a known value and you have some known boundary condition at the bottom. So that's why it's called a 2-point, namely surface and bottom, boundary value problem. And in general, 2-point boundary value problems do not have solutions, because let's say, let me just cook up one here. Suppose I have differential equation dy d, or whatever my function is, df dz equals, I don't know, e to the minus z. Well, okay, turns out this would just have the solution f would be equal to e to the minus z. Now, I've got a condition at the surface, so maybe at z equals 0, I want to have f equal to some surface value. So I'm going to have a constant here, and then I say, okay, when the depth is 0, f has to be the surface value, so that's equal to f naught. And then I say, well, maybe at z equals 10 meters, I want f to be equal to 3. But now I take this, I plug in 3 here, I plug in 10 meters, I don't get 3 back, because that function just doesn't fit it. In other words, I've decided here's depth, and here's my function. It's equal to, here's f naught at the surface, and it's going to decay exponentially. And at 10 meters, maybe this exponential decays down to a value of 1, and I'm saying at 3 or 10 meters it has to have the value 3. Well, the function doesn't satisfy that. Now, if I put in the boundary value problem at 10 meters, f has to be 1, and then I would say, oh, look, I can satisfy both boundary conditions, life is good. So anyway, in general, 2-point boundary value problems don't have a solution. But I know that this equation does have a solution. How do I know that? Trick question. Because light propagates through water. If this equation didn't have a solution, light wouldn't propagate through the water. And it does. So I know some way I'm home free. Okay, enough said about that. In general, to solve the radiative transfer equation, you have some region you're interested in. It's the ocean, it's a cloud, whatever. You have to know the radiance coming in, and you know the IOPs inside your medium. In the ocean in here, we're going to stretch this region out, make it horizontally homogeneous. The incident radiance will be the sky condition. The bottom can be either finite with a fixed reflectance, or it could be infinite and the light goes to 0. Anyway, it's a 1D problem, and that's what we work with in here. So I'll just walk you through a couple of solutions, trivial ones, of the equation. So suppose we have homogeneous water, so the IOPs do not depend on depth. We have no scattering, so the volume scattering function is equal to 0. There's no internal sources, so the source is 0. It's infinitely deep water. There's no radiance coming up from the bottom or anything, so L is going to go to 0 as depth goes to infinity, and the incident radiance at the surface is going to be specified just below the surface. Well, if we go back to our equation, there's no source, so that's 0. There's no scattering, so that's 0. There's no scattering, beam C is just the absorption coefficient. Okay, so we end up, whoops, wrong direction. We end up with the equation to be solved is just our depth derivative term minus absorption times the radiance, and all that other stuff was 0. Well, this guy, I just divide through by L, and I multiply through by Z, and I integrate from the value at the surface down to the value at some depth of dl over L, and I integrate from the surface down to the depth Z of absorption times dz divided by the cosine of theta, and I'm looking just in one direction here, and A is constant because the water's homogeneous. So dl over L integrates into the logarithm, and this guy is just going to give me A times Z over cosine theta, and so I take the anti-log and I get that the radiance at depth Z is the value at the surface times this e to the minus AZ over cosine theta. What's that? That's just Beer's law, right? So there's where Beer's law comes from the radiative transfer equation. Does this solve or satisfy the boundary conditions? Well, if I put in Z equals 0, that term is 1, and the radiance at 0 is equal to this initial value that I'm given. If Z goes to infinity, A is positive. I'm looking at light going down. Theta equals 0 is going down, so the cosine's positive. So this exponential is going to go to 0 as depth goes to infinity. And so then the radiance at infinity goes to 0. So I've solved the equation throughout the medium. It satisfies the two boundary conditions at the surface and the bottom. Life is good. I'm done. Okay. Next little thing, this fellow Gershon, who's a Russian, did a lot of work back in the 1930s, and he derived this thing called Gershon's law. And a word about Gershon, he was the first person to realize that radiometry was on shaky ground. And he published something like 100 papers, more than 100 actually, plus a book. As far as I know, the only thing that's been translated into English is the book. And the opening sentence of the book says that radiometry has been in a state of arrested development since the 1700s, that's Lambert and Bouguer, while the rest of physics has marched onward. And he tried to put radiative transfer theory on a solid physical basis, and he couldn't do it. Then this fellow Preisendorfer came along, and he worked for like 30 years, and he couldn't quite do it. And then Mischenko finally was able to get from Maxwell's equations to the RTE. Okay, so what Gershon did, though, is he started out with our friend, the 1D radiative transfer equation, and then he says, let's integrate over all directions. So I'm going to take the left side here, and I'm going to integrate theta and phi over all directions. So theta 0 to pi, phi 0 to 2 pi. Okay, well, these are integrals over directions, so I can interchange the depth derivative, which doesn't depend on direction, and the integral over direction, and I get a depth derivative of the integral of cosine of theta times radiance integrated over solid angle. Okay, so if I break this up into two integrals, 0 to pi over 2 of L times cosine theta integrated over that, what's that? It's the definition of downwelling plane irradiance. And then I'm going to integrate from pi over 2 to pi. Well, now the cosine is negative, so this is minus the integral of L times cosine theta. Well, that's minus EU. So what this left term turns into is the depth derivative of ED minus EU, which is the net irradiance in the vertical direction. Okay, so now we go to the next term here. And he says, well, we integrate this thing. Okay, beam attenuation doesn't depend on direction, so it can come out. and then we have the integral of the radiance over all directions. What's that? No cosine factor. That's just by definition the